Okay, let's start. Are there any questions from last time? So yesterday we did de Sitter spacetime, its structure and its various interesting coordinate systems. We saw that in many coordinate systems it looks like a cosmology, which means it's evolving in time, it's time dependent, but there are also coordinate systems where it looks static, but those coordinate systems don't cover the whole space-time. So the space-time was always defined. What is the full space-time is the one given by the embedding equation. After that, it's up to you to try and cover all of it or some of it with coordinates, and that's what we did. There's one little thing to clarify from yesterday. First of all, this equation I wrote is correct. So I made this is in finding the conformal coordinates for de Sitter. You remember that I made a change of variables from t, which were the global coordinates, to t tilde, and then we were able to factorize something from the metric and get a compact unphysical space, which gives the Penrose diagram. So now t goes from minus infinity to plus infinity. It's just the time of de Sitter space time in the global coordinates. What should be the range of t tilde? It's slightly tricky because both of these are even functions. So for half of t and the other half of t, this takes the same value. So actually cosh, as you know, looks like this, where this is 1. And cos looks like this, where this is minus pi by 2, and this is pi by 2, and this is also 1. Okay. So in order, sorry for my awful drawings, in order to cover the full space, we need to take this full interval. Okay. But actually, we could have flipped it if we just wanted to make our lives miserable and said that t tilde goes from there to there. It would still solve the same equation. So we just have to think a little clearly, but once you do that, you see that it's actually this region which maps to this region. And if you just take 1 upon this thing, you can see that 1 goes to 1 and things which are going to 0 will go to infinity. So it's a very simple map. Today we'll see a very similar map, but it will not cover the full region. So I just wanted to clarify this from yesterday. Are there any questions about this? So I should emphasize that in all studies of manifolds, it's very important to be clear when you have coordinates, what are their ranges, because a simple change of the range can make a big difference to the geometry. Okay, so today's topic is anti-de Sitter spacetime. The first thing to say about this is that there was no person called anti-de Sitter. This is also not the auntie of de Sitter. This is de Sitter's metric, but with a sign changed. And the way it arises, we like to find these by embedding something. So this time what we do is that we take in the embedding space, not just one time-like direction as we did before, but 2 time-like directions. And then the remaining directions are d minus 1 in number, and they are space-like. So this is a space of signature 2, d minus 1. Okay, so this is the embedding space. As usual, we first define the embedding space, then we define the embedding, and then we reduce to the space which satisfies that embedding equation, and that's our interesting space, or space-time as it happens. So this is the embedding space. And the isometry group of this is O d minus 1, 2 because of this double negative signature. Okay. Now the constraint equation, so yesterday I called it a constraint equation. I think the correct name for it yesterday as well as today is isometric embedding. So you can of course embed anything you like in this space-time as long as it embeds properly, but there's no guarantee that what you're embedding will have the isometries that this thing has. But if you're careful about what you embed, then it will have. And manifestly, in yesterday's example, we wrote a metric of an embedding space and a constraint equation, both of which had the same symmetry manifest. Therefore, that was an isometric embedding, and today we'll also do an isometric embedding. But for that, we realize that since this has signature 2, d minus 1, the embedding also has to have that. So we need to say that minus x0 squared minus xd squared plus xi squared from 1 to d minus 1 is a constant. This is an isometric embedding manifestly, and the constant can have either sign, but we choose it to be negative. Yesterday we kind of stated some general principle which is very easy to convince yourself of, that if this is negative, then one of these two negative directions will be killed and we'll get space-time of signature 1, d minus 1, which is what we always want. We can take this to be positive, then we'll get a space-time of minus 2 of 2, d minus 2 signature, and you can do whatever you want with it. There are people who work on physics theories with 2 times, but they're not very popular. Some people refer to them as a waste of 2 times. Anyway, so good. Now, so what's the procedure next is always to solve the constraint. Yes, please.
Is there a reason why changing just one sign from the de Sitter is causing the change of the overall space itself?
It's a fact.
Can we
Yeah, well, I can give you, as we proceed with today's lecture, you will see many ways in which that fact manifests. But I can just give you one if you like, which is that cosh is not a periodic function, but cos is a periodic function. And if I send some coordinate to I times itself, then its cosh will turn into a cos, but periodic functions are completely different from non-periodic functions, and trigonometric functions are different from hyperbolic functions. But that's really just understating the difference. The difference is quite big, and I think it's a very good question you have raised, but I'll ask you to figure out the answer from what I'm doing today and what I did yesterday. Just look at it side by side and ask yourself what are the key points where the geometry differs. Of course, because the geometry differs, the physics will differ. But we are not doing any physics. We have actually done no physics since the start of this course, and we won't be for yet some more time. We're just doing geometry, Lorentzian geometry. But yeah, good point, and you can be attentive to these questions as we go along. Now, as I said, normally we try to solve the constraint right away in different ways and write down different coordinate systems, but we can do something else right away. So, what is a constant time section? In de Sitter, that was not difficult to understand because there was only one time in the embedding space. So we could just set that time to be a constant and we would get something, and we would get a sphere, and that made us happy that the section is a sphere. There's something a little more tricky here because there are 2 times. So we don't even know what time we want to keep constant. Which of them do we want to keep constant? But we can understand that by the following idea. These two generate a 2-plane of time-like directions. Now in a 2-plane, I can have polar coordinates. So let's go to those polar coordinates. x0, I'm still in the embedding space. Okay, if we do this, then the metric of the embedding space becomes minus r squared dt squared minus dr squared, and then the rest is unchanged. Yes.
If our embedding space is the Minkowski space, can we do something like, can we define a locus, can we vary all possible locuses to get every possible metric which solves Einstein's equation?
Let me understand. First of all, our embedding space is not Minkowski space time
Not-
here. Yeah.
suppose
Suppose
we
it
have-
was, okay.
We can find all possible constraints on
No,
the
no,
particles.
not everything cannot. For example, a black hole, as far as I know, is given by a metric, but I can't write an algebraic equation which gives me the black hole metric. So, first of all, most space-times are not isometric embeddings. They don't have the isometries of some underlying higher dimensional thing. So, it's a very special thing of maximally symmetric space-times that we can write there, we can study them, define them, and also study them in this formalism using one higher dimensional embedding space. Yeah, there's a question.
Are we trying to t as a time coordinate?
Coming to it. So you see that this metric, I've just rewritten that metric in different coordinates. It still has 2 times. Okay, but now I've done it in such a way that we can ask the question, what if we treat this as the time? Okay, so if we want to treat this as the time, then we should set dt equals 0, then we get the fixed time surface. Okay, so sorry, actually I didn't want to write I'm being a bit this thing. This is the metric, yeah, this is the metric. But let's first write the embedding equation. So the embedding equation, which is the second one, is similar to this. It is actually similar but not identical. In the embedding equation, of course, t disappears because x0 squared plus xd squared by definition is r squared. So it's minus r squared plus all this is minus l squared. So we have that metric and we have this embedding equation, and now what you can see is that this is independent of time, and so there we can set dt equals 0 to have a fixed time surface. So this is the equation of that fixed time surface, and in fact it looks very much like the equation we used to define de Sitter, except that this is negative. This being so, this negative sign will cause this negative coordinate to disappear, and we'll get a positive signature space because we are looking for the space. So we simply chose to interpret t as the time, it's our choice. Okay, and in that interpretation, this is a spatial hyperboloid. So we've learned a valuable lesson that de Sitter space time at fixed time, at least in one choice of fixed time. Remember, there's never any unique choice of coordinates. So anything you do in one choice of coordinates will teach you something, but you can't say that you're learning something better than what someone will learn in some other choice of coordinates. But this certainly teaches us something, and actually it teaches us 2 things. So spatial hyperboloid is the constant time section in this description. It's a hyperboloid, so it's not compact. It extends to infinity. Very different from the constant time section of de Sitter, which is a sphere, and therefore it's compact. Again, partially answers your question. If I have an equation where all the signs are plus and the right side is plus, I get a sphere, and that's because when everything is plus, it has to be bounded, because any of these terms becoming too large will cross the right hand side and there can't be any solutions. But if there's a negative sign, then whenever these become large, this can also become large, and the whole thing can be still negative, and so it's non-compact. It goes off to infinity. It's really the difference between in ordinary coordinate 2D coordinate geometry, that and this. It just differs by I, one of the coordinates going to I times itself, but it's a huge difference. Maybe I need not expand on this too much, but roughly the Earth does this orbit, but if the Earth was doing this orbit, life would be extremely different. Likewise, a comet, for example, would do this orbit, but if it was doing that, then life would be different. So it's really important, the difference. Okay, so that's one lesson. There's a second lesson which is quite weird, which is that T is periodic. Because we defined x0 and xd in terms of a coordinate which is defined through trigonometric functions, and so as t goes to t plus 2 pi, x0 and xd come back to themselves. Okay, even if we didn't know how we did this, if you just stare at that metric, minus r squared dt squared minus dr squared covers a plane only if t is periodic, otherwise it doesn't.
X0 and xd is periodic. T can be anything.
T is a periodic variable, by which I mean that the variable that I mean that means the values of t have to be restricted between 0 and 2 pi. X0 and xd can take any value because r is there. Since r can vary freely, x0 and xd are periodic functions of t, that's what you're saying, I agree with you. But x0 and xd together cover a plane, entire two plane. And how do they cover it? T makes a circle and then r makes a line, and as you stack all the circles, you get the whole two plane. Okay, but t alone is periodic in the sense it's angle valued. If you want the very precise statement, it's angle valued. If you keep counting all values of t, you will simply keep repeating many copies of the x0 xd plane, which is not what you want to do, because the original. Yeah.
This is just some manifestation of the parameters.
No, not necessarily. Not necessarily. Again, as I told you earlier, whatever you find to be true in one coordinate system is a true statement. This coordinate system doesn't have any deficiencies. It doesn't cover half the space. It doesn't cover double the space. It covers the original space. Any property we find in this coordinate system is going to be true in general.
But yeah, just one more thing. So R can also be treated as time, right?
R could be treated as time, yes.
And T can be some.
Well, the point is that in the embedding space there are two times. You're not going to get rid of one of them. So we still have. So this is a little bit early discussion, but it's just before we actually go to correct coordinates. But just to show you that t comes out angle valued in doing this. Then we'll use similar things. See, right now we did something very partial. We just rephrased x0 and xd in r and t. We didn't solve the hyperboloid equation. Next we'll do that. But for the moment, we just know that this is periodic. And this already creates a disaster, which are called closed time-like loops. The space simply comes back, the space-time simply comes back to itself after 2 pi evolution of time, of this time. Okay? That means we expect that in any coordinate system, there will be a time coordinate which will come back to itself after some finite time. And this violates causality, because now you can go back into your own past. Okay? So the absence of closed time-like loops is considered an absolute requirement in any theory of gravity. Otherwise, we don't have a causal description. And to make it go away, we have an option. Notice that a closed loop is like a non-contractible cycle, and that means the space has a pi1 homotopy, and it's not simply connected. And there's an easy way to make any non-simply connected space simply connected, which is to unwrap it. That's called going to the universal cover. So we can go to the universal cover. We just declare that we are going to study not the space-time that came by this embedding manifold and its constraint equation, but a new one which is obtained by taking the old one and stacking it on top of itself infinitely many times. We have to declare that.
In order to avoid closed time.
In order to avoid closed time-like loops, and it very successfully does so. So, and luckily it doesn't require anything. It just says go to any coordinate system which has the closed time-like loop and then just extend t by hand to go from minus to plus infinity. Yes?
So like the universal cover can be for any, like it's a general property?
It's a general property that you can always go to a universal cover of any manifold which is not simply connected, and the universal cover will be simply connected. The problem though is that then the universal cover will be something like infinitely many copies, so it could be quite different. For example, the universal cover of a circle is a line, is the real line. And if you want to think about how well we understand that, well, time of our lives is measured on a real line, but we have this weird thing called a clock which has vanished from that wall, which actually goes on the circle. Okay, and we follow a convention that 12 o'clock tomorrow is not the same as 12 o'clock today, though it's the same on the clock. We agree that it's not the same because we have unwrapped that clock into a long thing, such that actually the clock is just measuring each segment of that longer infinite time. It's just the same.
Isn't that like just like after every period we just attach the line? Like so, yeah, it's just a copy of that. In front.
It's just a copy. It's just a copy. I'm just emphasizing that the way we find out that the next day's 12 o'clock is not today's is because our parents will slap us if we try to say the opposite. We don't think about universal covers at that time. We are 4 or 5 years old. Okay, I hope parents don't slap anyone, but metaphorically, they tell us to do it and we obey. But really, what they are telling us, and which they also may not realize, is to go to the universal cover of that clock. That's our actual time. Good. Okay, what about symmetries? So we are just delaying going to coordinate system as long as we can. So the obvious symmetry of the covering space is OD minus 1, 2. Okay, and we will see repeatedly, this is maybe I am stating this a bit prematurely, but there's a D minus 1, 1 dimensional subspace of or subgroup which we can realize linearly. It's not very surprising because this part follows more or less the rule of analytic continuation, because one of these two was that side in de Sitter and this also was that side in de Sitter, so you can do the same kind of game as in de Sitter. And so actually ADS is this quotient. It's a homogeneous space again, and these are linearly realized. Of course, it's an unwrapping of that quotient. The quotient gives you the original ADS with the compact time direction. But here there's one new illumination. This is the symmetry or isometry group. Is the Lorentz group. That was not the case for D-dimensional Minkowski. That was not the case in de Sitter. And this fact has been known, I'm sure, for at least a century, but probably people didn't stare at this relation and say how nice it would be if this was related to the fact that there's a holographic dual theory on the boundary, but that is the reason. This is why I brought up the subject of the linearly realized symmetry. The homogeneous space structure and the fact that there's a linearized symmetry gives me some chance of or gives me some hope that on the boundary of anti-de Sitter space-time, there'll be a space-time of this dimension, one lower than that. And what is lower is this is the symmetry group. This is not the signature of ADS, but the total dimension is lower by 1, and that this one, which is linearly realized, will somehow be associated to a field theory on the boundary. Well, that idea is only 28 years old.
Why was this not in DS?
Not in DS because in DS what did we have? We had, I believe, OD, 1 over OD. So yeah, you could, of course, that is the basis of, it's much more artificial. In de Sitter, we look for a boundary at, first of all, in de Sitter, as you know, the boundary is at time-like infinity, future and past. So there are two boundaries, they're not connected to each other. And people who try to do DSCFT are in fact trying to put a Euclidean field theory on the boundary. But remember that a Euclidean field theory is not a field theory, it's some kind of thing.
But that's still conformal. That the field theory living on the this time
Yeah,
length.
we haven't, yeah, I mean it will have the de Sitter group as its symmetry. It's not going to be, it's not as I said, it's not a field theory, it's not a Lorentzian signature theory. It's a Euclidean version or Euclidean rotation of a field theory. Of course, you can do a lot of things by Euclidean rotations of this, which means generally sending some coordinate to I times itself. But, it changes physical things. For example, in the case of de Sitter, as I said, the boundary is up and down and it's disconnected. We'll see that in ADS the boundary is on one side and it's completely, in actual ADS it's connected. So things are very different.
Also,
Yeah.
the non-linear transformations here
Yeah.
are the conformal transformations.
Yes.
Also, sir,
Yes.
I think de Sitter also had the equation being divided by OD minus 1
Was it? I forgot what it was.
Yeah. Because XD
yeah.
was solved to be the square root of L square plus x naught minus xi square. So that was.
Let me just think. I hope I didn't write something wrong. It's always possible though. Let me just see what I claimed. OD1 over OD minus 1 is what I wrote. Yeah, I think I did say that. Good point. OD1 over OD minus 1. I hope that's correct. Is it correct? Yeah, it looked correct as you say.
Because the solution is.
Yeah.
But what is the problem?
The problem is that if, I'm sorry, I'm just a little confused right now, but here what happens is that we have a Lorentz group and we are going to find a boundary of Lorentzian signature. And this will be the symmetry group of that boundary. But in de Sitter, apparently we have a Lorentz group, but our boundary is of Euclidean signature. I don't know, I'm just worried that that's not making sense to me. Does it make sense to anyone? Let's not dwell on it because this is going to go on YouTube and people will have to share our confusion. We'll talk about it after the lecture, but it's a very good point you made that the denominator actually I wrongly said was OD, but it's actually also OD minus 1, as per what I wrote. I'll double check that. One can get these things wrong. Good. So having postponed this for a long time, let us now finally write some coordinate systems. And the procedure is going to be not so different from what we did for de Sitter, and if there's one thing I'm quite happy about my notes because I really struggle with this, that we somehow are trying to discuss Minkowski, de Sitter and ADS, anti-de Sitter all together. Unfortunately, most of the existing reviews discuss one of these because they want to immediately apply it to one problem, which could be ADS-CFT or it could be DS-CFT. And here somehow we'll try to put them together. For me, one advantage is it helps one remember also more clearly what is going on. At least only after I made these notes, I could, if you wake me up in the night, I will be able to tell you what is the difference between 3 Penrose diagrams. And I think a few months ago, I couldn't have done that so quickly. Okay, so here are the coordinates that we propose, global coordinates. We take x0. We already said it's nice to have a cos t in it, but we didn't give any details of what multiplies. We just gave it some name r. Now we'll call it a number L, which is that number in the constraint, times cos of some coordinate rho. And xd, we have to put the same thing, remember, in order to get that polar coordinate structure. So we've done this, but now r has been replaced by L cos rho, and the remaining xi's will also be parameterized in terms of rho in such a way that the constraint equation is solved. So now we are finally trying to solve that. It has to have an L. It has, again, no surprise, a unit vector, and then it has sine hyperbolic of rho, and I goes from 1 up to d minus 2, d minus 1. So these are of course d plus 1 coordinates, but on the right side we get only d coordinates because there are d minus 1 of these unit vectors, but since they are unit, there are only d minus 2 angles which describe them. So these parameterize a d minus 2 sphere. Add to that rho and t, and we have d coordinates of anti-de Sitter.
There we said R was lying between 0 and infinity, but here cos h rho will rise from 1 to infinity.
Yes, but that actually doesn't matter so much because these can be 0. Okay, so let's see if this causes a problem. You're saying, for example, what if I want to reach the point x0? That's the point. So you see, from the original constraint equation, you see that x0 and xt can't be both 0 because then this side is positive and that side is negative. So they can't simultaneously be 0. But now the question is whether they can simultaneously be very small. Can they be arbitrarily small?
No, they can't.
Yeah, because the whole thing is minus L squared cos squared rho. So question is, but sorry, what did you say? No, they can't.
Same.
Exactly. They are bounded by minus L squared. If I bring this to the other side, this sum has to be greater than L squared. Yes, thank you. That's exactly the point. And that's achieved exactly by this. So the embedding equation already imposed that constraint on x0 squared plus xt squared. Thanks for the question. Okay. So with all this, our metric is now, it has an L squared in front of everything, minus cos squared rho dt squared plus d rho squared plus sine hyperbolic rho squared of rho d omega d minus 2. So we have a d minus 2 sphere, and then we have this structure, and that's it. What is the range? Rho is greater than 0. T, now notice that it has come from an honest change of coordinates and it's a periodic angle valued variable. So 0 less than equal to t less than 2 pi with periodic identification, and that's it. The angles are the angles of the sphere, nothing to say about them. But this gets a name, it's called the radial coordinate. And I was just being very fussy to do this properly for anti-de Sitter, but as soon as we go to the universal cover, we simply cancel this requirement and write minus infinity less than t less than infinity, and we are done. So we just have to use words to go to the universal cover. We'll see that it will reflect in the Penrose diagram. Okay, so what's the topology of this space-time? So again, it is initially, sorry? Yeah.
No, I was just saying it's similar to st minus 1.
No, actually it is R, that whole thing forms something which is topologically R d minus 1. And so initially S1 cross R d minus 1, and the universal cover is just RD, R1 cross RD minus 1. Okay. And now onwards, I think almost always we will mean the universal cover, but if we don't, I'll make it very clear.
Sir?
Yes.
Sorry for the, like, I don't see how does that part correspond to topologically RD.
It's sort of a hyperbolic space. So
Yeah, because instead of sine, it's a sinh.
So when the point is that sinh squared rho, when rho is very small, is rho. Sinh rho is rho when it's very small, and that's the only place where there might be a problem. So at very small rho, that's a d minus 1 plane. That you agree? Because d rho squared plus rho squared d omega squared is a hyperplane, it's Euclidean space. Now all that we are saying is that as rho goes out, that space is just expanding. It doesn't change its topology. So it's not a flat Rd minus 1. It's very much a curved Rd minus 1. But in fact, it's nothing but the spatial section I told you earlier, which as we now know is a hyperboloid. It's the same thing. And a hyperboloid is something which is sort of going away to infinity and expanding. So that's what it's doing. So only topologically. Of course, the topology doesn't tell you much. For example, as I said, it's not the flat Rd geometrically, but secondly, it's not even a direct product of R and Rd minus 1, because the R part of it, which is the time, has a space dependence. The time is also expanding with space. Yeah, there's another question. Any other questions? Okay. Okay, now easy thing to do. We can calculate given one set of coordinates. Oh, first comment is that these are static already. So there is no need to go around hunting for static coordinates. And moreover, del by del t is a killing vector. T simply doesn't appear in it. So it has a time-like killing vector everywhere. There's a little exercise somewhere which tells you the norm of this time-like killing vector. I'll tell you right away. Its norm is minus rho minus L square cos square rho, which is always negative, so it's always time-like. So that's that. Okay. Next thing is to calculate curvatures. Well, the formulae are quite trivial. They're just the minus of whatever we found with De Sitter. So, sorry.
What does the norm of the killing vectors tell us?
It tells us whether it's time-like or space-like or null. If the norm is negative, it's time-like. If it's positive, it's space-like. If it's zero, it's null. And I'll be talking a lot about norms. When I talk more about geodesics, we'll go into norms. But already we did discuss geodesics, and those geodesics could be time-like or null, and we didn't consider geodesics which are space-like. So for them, the tangent vector is the one whose norm I wanted, not necessarily.
But here one side, right?
Yeah, so this is all time-like. But also in geodesics, we argued that for a geodesic, the norm is always has the same sign, so it must be always, if it's time-like, it must remain time-like. Here, these are not necessarily geodesics, just like those were not necessarily isometries. Okay, this is an isometry, that's the main point. That's the only point that's of interest now. Okay, so the Ricci, we start by calculating the Ricci scalar. It comes out to be the same as for De Sitter, but with a minus sign. And I don't have to write the Riemann and Ricci tensor and Riemann tensor because they are the same again as the last time, but with a minus sign. And so eventually we find that the cosmological constant for this space is minus d minus 1, d minus 2 upon L squared, and is less than 0. There's upon 2L squared. So there's nothing, no change in the calculation. I mean, once you get this one, of course, you have to calculate in some coordinates. So there's a bit of work to write down all the Christoffel symbols and all in those coordinates, calculate it, but once you've done it, you've done it. Okay. Now, considering that these coordinates were already static, it's a bit odd to talk of static coordinates, but there is something in the literature called static coordinates. But it's not going to be They are going to be as just the same as the global coordinates with a almost trivial change, but it's a change that will be useful for the future. All we do is redefine rho by saying that this is a new coordinate sigma, and for tau we absorb the factor of L radius into t and call this tau. So this is a trivial change by scaling, and this one simply replaces sine hyperbolic by sigma. The virtue of this is that we get the metric in the following form. We get f of sigma d tau squared plus 1 over f of sigma d sigma squared plus sigma squared d omega d minus 2 squared. So all mention of explicit L has disappeared, but of course it can't just disappear. The function f is 1 plus sigma squared over L squared.
So there is a rise in here.
Sorry, where, what?
Oh, sorry.
Yeah, it's if anything, it looks maybe more like a Euclidean black hole. It doesn't have a horizon, but it has a L dependence, and the important thing is that it has the function up here and down here, and that is a little bit black hole-ish looking, and it will turn out to be a useful thing to define the Schwarzschild ADS black holes.
But F sigma never goes to 0.
This one doesn't go to 0, but once you have but there's no black hole either, so it shouldn't go to 0, otherwise we wouldn't know what to do with it. I mean, there's no reason it should go to 0, but if there was a black hole, there could be one more term. We could just modify f by one more term, and then it could go to 0, and then everything follows from that. So it's just good to prepare this metric for pure ADS so that we can use it later. That's its main purpose. Okay. Now, just before coming down, I noticed that Hawking and Ellis actually have a time-dependent metric for ADS. You can do that. There's never a problem to make the metric look one thing or another. But I'm not going to go through it here. You may look it up. I will add it into my notes at some point. I didn't have time to work out how they arrived at it. But again, here what happens is that time-dependent metric only covers half the space-time. In DS it was the opposite. The time-dependent metric covers it all. The static coordinates only covered half the space-time. Good. Okay, now there's a quite non-trivial new set, but again the end result will be something quite similar to what we already know, already did yesterday for de Sitter, which are the planar or Poincaré coordinates. And there the goal was to make a d-1 hyperplane manifest and have it be expanding in time. Here we are going to make a Minkowski space-time manifest and have it be expanding in space. It's very similar and yet not the same. Okay? And these coordinates will actually cover only half the space-time. So for this, I'm going to first rewrite the embedding equation. In the following form. I'll write it as eta mu nu x mu plus xd minus 1 squared minus xd squared equals minus L squared. What have I done? First of all, xd squared is just doing what it was doing before. There was a minus x0 squared, that's there, it's just here. Okay, and out of the xi squared, I've just picked out one of them, one space direction. Okay, so earlier I had bunched it as 2 time-like and d-1 space-like. Now I have bunched it as 1 space-like, 1 time-like and d-1 Minkowski signature. Okay, so here mu goes from 0 to d-2. So I just rewritten the equation. Now what I want to do is to define new coordinates by saying that x mu is equal to L, the ADS radius, times an exponentially growing factor. Reminds you maybe slightly of the e to the t factor we had yesterday, times some coordinate small x mu, which are the coordinates of a fixed which will be the coordinates of a fixed flat Minkowski spacetime. So this is what I want. Okay. Now I state this as my intention, and that determines all of these. So I only have to solve the equation for those. So with this, I find that xd squared minus xd minus 1 squared, I take both those on the other side, should be L squared, which has come on the left, plus the square of this. So when I say x squared, I mean the Minkowski square x mu. So this is L squared into 1 plus e to the 2 rho x squared. Now it's an easy equation to solve. All I do is notice that xd squared minus xd minus 1 squared factorizes as xd minus 1 times xd plus xd minus 1, and each of them I'll choose something which I like. So xd, this is a choice. This completes the change of coordinates. X mu we did already. So we are going to just declare that this is equal to e to the minus rho, that factor. And something I did wrong.
Maybe L as well?
Yeah, I've lost some L somewhere. No, I haven't actually. xd minus 1. No, I have not made any mistake, I think. This is going to be L squared e to the rho. So if I multiply these, I should get that. So this cancels this prefactor, and L squared comes in its place, and I get exactly what I want. So now I can solve this for xd minus 1 and xd, and that will complete the change of coordinates. So xd minus 1 is now, it's just the sum and difference. It's not very exciting. Half, but just to help you stare at it. Just a little tedious, so nothing very complicated going on. Okay, so these two plus the equation that just disappeared up there are the final change of variables, and our final coordinates are x mu and rho. Now one thing to notice here is this equation. So notice that this stuff is positive, L squared times e to the rho. Therefore xd has to be greater than xd minus 1. So that's a half space. Of course, you can see it also from this, because xd has a term, positive term plus, and xd minus 1 has the same term with a minus. Okay. Yes. Good. And what's the metric finally? It is L squared. The metric is very simple after all these manipulations. Plus e to the 2 rho eta mu dx mu. It's a really cool choice of coordinates. It's exactly what I asked for. This is a Minkowski space-time volume element, space-time element, and it's expanding. And how is it expanding? With rho, which is the radial coordinate, and which starts at 0 and goes out to infinity. So it's just a Minkowski space-time that near rho equals 0, it's very small and it's just getting bigger. And of course, this metric, of course, the linear symmetries are manifest. OD minus 1 comma 1 is clearly visible. I'm beginning to think more and more that I said something wrong yesterday. For de Sitter, the static coordinates, don't they have XA in them? That should mean that OD is the linear group, linearly realized group, and not OD minus 1 comma 1. No? Just look at, if you have any notes, look at them. I'm pretty sure yesterday I had XA, right? So that was playing the role of this. XA was the d-dimensional thing that was expanding. Am I wrong?
Minus dt square plus e to the power 2t xx.
XX. So that was d minus 1 dimensional. This is also a d minus 1. Okay, maybe I'm saying too many things and mixing them up. This actually is a d minus 1 dimensional Minkowski spacetime. So it has actually d minus 2 comma 1.
D minus 2 dimensional.
Huh?
D minus 2 dimensional.
No, this should be d minus 1 dimensional, because I said that mu goes from 0 to d minus 2. 0 to d minus 2. So it's d minus 1 dimensional as a space-time. So always so one of the confusing things in the literature is that half the literature that we read is prepared for ADS CFT correspondence. So already the CFT has some D, so then the ADS has to have one higher D. In my lectures, all manifolds that we want to study have dimension D of space-time. D minus 1 of space and 1 of time, that's it. And anything that has a different dimension might be an embedding space or a subspace, but it's not the manifold that we want. Okay, good. So we've achieved a nice metric for ADS, and as you might guess, there's one more metric coming up, which is going to be the one more choice of coordinates, that's going to be the conformal coordinates. Okay, there are a few remaining comments to make about this form of the metric. Notice that this has this interesting feature that if rho goes to rho minus log alpha for some constant alpha, then this gets a 1 over alpha squared. So I can scale the small x to alpha times x. So this is a symmetry. So we see some characteristic things that by now all of you have heard about the physics associated with them, but we are simply saying that with the logarithm, because of this exponential, with the logarithmic amount of shift in the radial coordinate, the transverse space-time of small x mu expands by that corresponding factor. Scaling, exactly. And another thing to say is that the time-like killing vector is d by dt again, but this time as rho goes to 0, it becomes null. Rho goes to minus. Okay, maybe I should first I'll change the coordinates again. So supposing I define r equals e to the rho, then of course this metric becomes L squared dr squared upon r squared plus r squared e to the eta. I can just call this x squared. X squared is shorthand for eta mu nu dx squared. Eta mu nu dx mu dx mu. Okay. Now of course we have a scaling of both. So if r is scaled by a factor, this is obviously invariant. Here r gets a factor, this should have the inverse factor. So it's more obvious. And there's yet another version where we define, so here as r goes to 0, which is the old rho going to minus, well actually it's not supposed to go to 0. Sorry. So why am I taking r to 0? R is e to the rho, r should start at 1. No? isn't it? Yeah. Rho is a positive coordinate, so R should start at 1. Yeah. Okay. Okay. There's another version where instead of, so this is 1 less than or equal to R less than infinity. Another version is just take Z equals 1 by R and you get L squared dz squared plus dx squared upon Z squared. We saw a similar thing for de Sitter, but in de Sitter what happened was that this one was time-like. Here what's happening is that inside dx squared there's a guy which is time-like. There has to always be one time-like direction, but it's not this one, it's in there. That's the only difference. And here infinity is then going to 0. So in the literature on ADS CFT sometimes we get confused because is the parameter radial coordinate going to infinity or is going to 0? Well, it's just the simple trivial inversion which you can do either one. And these are the typical what are called Poincaré metrics. So they have a hyperbolic nature, and if I just in my mind did a Euclidean continuation, which is actually valid and defines what is called EADS or Euclidean ADS, then this is called the hyperbolic plane or hyperplane. If there was a single x, then this is a metric on the 2-plane, which has this form you might have seen, which the distances get shorter and shorter as you go up. And then you might know there's a conformal map from that to the disk, and then suddenly some birds appear and there's a Escher picture. You must have seen all those things. Okay, good. Okay, that brings us to our last topic. Any questions? All clear? Good. So our last topic for today is conformal coordinates, and these are always accompanied by a Penrose diagram. And well, by now we know the idea very well, and we have our metric, global metric. We always start with that, and it was minus cos squared of rho. Now I am going to make rho a function of a new coordinate theta, and I will find that coordinate. The next term is supposed to be d rho squared, so this is minus cos squared rho d t squared. The next term, which was d rho squared, I'll write as d rho by d theta. So it's just a single variable, so d rho by d theta squared, d theta squared. And then the last term is sine hyperbolic squared rho of theta d omega d minus 2 squared. So this is after a change of variables, which I haven't yet figured out what it should be. Rho goes to a function of a new coordinate theta. Now what we want is to make this term cos squared of rho and this term the same. It's the same manipulation as yesterday and it has the same solution. So we require that d rho by d theta should be cos rho. And we integrate this equation to find that cos rho is equal to 1 over cos theta. Exactly the same as yesterday. This was t and this was t tilde, and it was t tilde which was giving me a finite range. But there's a crucial difference because rho is only greater than or equal to 0. It doesn't go below 0. So I only get half of the cos region. So for example, cos as we saw was this. So I have to keep some half of it. And which half do I want? I think the right half. So I just cancel this and I keep this half. half. It's an even function, so I can keep either half. Okay. Then for theta also, I have to keep only this half and not this half. I did this argument earlier, and so it follows that 0 is less than theta is less than pi by 2, and actually it's less than or equal to theta less than pi by 2, where pi by 2 is the place where 1 by cos diverges, so it's where rho has gone to infinity, so that's asymptotic infinity. And just to be very picky, I use less than rather than less than or equal to, because rho equals infinity is not a point, it's an infinite, it's infinity. But in a moment, we'll do the conformal compactification, we have to still do it. Once we are in the unphysical compact space, then we can restore an equality here, because now we can actually reach the boundary. That's the whole point of Penrose diagram. The boundary is an unreachable place. You factorize something from the metric which takes away that infinity, and now the metric you simply continue it by hand to the boundary. So we have to first see how to factorize this out. Yeah, so you might worry what happens to the last factor, but actually it works out fine. So we get ds squared is equal to L squared upon cos squared theta. This comes out from the first two terms, minus dt squared plus d theta squared. Now in the last place, we had sine hyperbolic squared rho, and we are taking out cos hyperbolic squared rho. So inside it is tan hyperbolic squared, which I believe goes to sine. So we get sine squared theta. This is a little exercise you'll have to do. So we get this. And looking at this, we should be delighted. This is the conformal factor which we are going to drop. This is the unphysical metric. And what space-time does it describe? Something awfully familiar. Einstein static universe for the third time. It's the Einstein static universe for Minkowski and for de Sitter and for anti-de Sitter. The only differences in the three cases are the ranges of coordinates. Everything, the geometry, local geometry is the same, but the ranges of coordinates are different. Why? Because now t, first of all, is going from, we haven't unwrapped it, so it's going from 0 to 2 pi. We will unwrap it soon, but it's worth keeping in mind that right now it's not unwrapped. Okay, theta goes from 0, now we can take it to pi by 2, and this is the unphysical space. I call it, deliberately I am giving it this ugly name because you have to remember that it's not real space-time, it's a conformal, a more polite name is conformally scaled or conformally compactified space-time. But please remember, it is not the original space-time, and that's why if you draw anything on a Penrose diagram, you might just come to wrong conclusions. You have to know what you're drawing and why, and what you can reliably get from it. Good. Okay. Yes, question? Okay. Okay, so with this we can draw the diagram. So different from Minkowski but similar to de Sitter, it's a square or a rectangle. That's a matter of detail. Maybe we should draw it as a rectangle because t is going from 0 to 2 pi and theta is going from 0 to pi by 2. So it should actually be much narrower than I've drawn it. But we shouldn't really argue about that because we are trying to capture some causal structure and all that. But we have to be a little more careful about each of these boundary lines. First of all, what is this boundary line? This is rho equals 0. And this is just it's not the end of anything, it's just a coordinate singularity of those coordinates. So I'll just draw it as a dotted line. What basically happens is that at theta equals 0, that sphere shrinks to 0 size. Just as it did in de Sitter, it just shrinks to 0 size. What about pi by 2? That's where the sphere has become a unit sphere. Sine pi by 2 is 1. In de Sitter, it was the sphere was growing till here and then shrinking back there, but it's not doing that now. It's just growing till here and staying maximal, and the space time is ending here. And this is the asymptotic boundary. This is rho equals infinity. So this is the boundary. And in the original coordinates, it was rho going to infinity. So it is actually the end of de Sitter, anti-de Sitter. What about up and down? Now something fun happens. They identified. So there is no boundary. There is no boundary at up or down. Any particle which is going like that, that will undergo a time-like loop and come back here and then continue to propagate. So particles will keep doing that. Certainly the massive particles, which will correspond to vertical or slightly curved lines, but which are predominantly vertical. Okay, so now we need to unwrap this if we want to get to, so this is for compact, this is for original ADS. I'll call it original if it has this time-like loop. Now I want to replace this and go to universal. Well, this is gone, 0 is gone, 2 pi is gone, and t simply goes for the diagram simply becomes infinitely down and up. Yes?
So this conformal compactification could also have been done in the Poincaré coordinates. It could have just removed the 1 by z square.
We could have done that, that's correct.
So that would have given potentially different Penrose.
It would give a different structure, however, it only covers half the space-time, and we use that also. Yeah, but that covers half the space-time, this covers the whole space-time. Okay, now something that most references don't remark on, but Hawking and Ellis in their wisdom do remark on it, though not in the words I'm going to use. This isn't a Penrose diagram. A Penrose diagram is supposed to fit in a finite space and time. This doesn't. It's infinite. So, but this is pointed out by Hawking and Ellis, and well, it's the fault of your unwrapping. There was never any problem to make a conformally compactified ADS if you were going to live with these closed time-like loops, but you have unraveled it and gone to the universal cover, and this is your price. And one thing they note, which is almost obvious, is that I could define some new coordinate which would squash this down. But if that definition has to be conformal. I can't do anything which changes angles. If it's conformal, then by squashing this down, I'll also squash this down, and all my space will get scrunched into a point. So that's pretty hopeless. You can't do it. So you just live with this non-Penrose diagram. And this boundary, Hawking and Ellis like to refer to it as scry without any plus or minus, because it's the only boundary in the story, and scry is generally a boundary where null rays go. And you can see, again, one has to show that null rays are at 45, but it's guaranteed by the fact that we did a conformal compactification, and so they will reach the boundary. So null rays reach there. What do time-like rays do? They go there, and they never end, but Hawking and Ellis's proposal is to put a dot over here called I plus and a dot somewhere here called I minus, and say these represent space-like infinity or time-like infinity. Well, I don't know what you want to call it. It's time-like infinity. And the point is that you can't draw a line saying there's a line of I plus, because that line would have to be at some finite place, but this I plus is actually way outside this building. And so, you know, when something's infinitely far away, we can think of it as just being a point. So that's it. And time-like curves, for example, starting at this origin in these coordinates, will go like this. More energetic ones will go like this. So as you can see, they'll sort of come arbitrarily close to the boundary, but not reach there, and null curves will reach there.
We can find the trajectories.
Yeah, all of them you can find. I'm not going to do that, but it's a very good exercise, and I'll put it in the next set of exercises. Actually, now there are many exercises. I hope some of you at least tried the previous set. I hope you even know that there is an exercise set. It's on the website. I think they are quite challenging, and one of them I don't know the answer to, so you can help me if you find the answer. And well, so I think we have said all that we want to say about the Penrose diagram of ADS, but definitely one can go through these coordinate changes. Nothing is very sophisticated about them. You can always find trajectories, let me just say, time-like. There's a lot of physics of these, both the de Sitter and anti-de Sitter Penrose diagrams, discussed in words in Hawking and Ellis. It's one of the few occasions when Hawking and Ellis lapse into 2-3 pages of words. Normally, they'll give you 2 equations which already take you a week to derive. But here they actually go into some physics description of what are all these curves and what do they do. They have some diagrams which are frankly pretty hard to understand, but and which they don't really explain too well, but they are there. But it's worth reading. So if you're interested in what I did yesterday and today, that's the reference. Strangely, many other references like Wald's textbook don't even discuss Penrose diagrams. And well, I'm sure that there are many references on the subject, but I think most of what you need is in Hawking Ellis, and of course I've gone through it. Okay, so this concludes our discussion, and a little early also, nicely, on maximally symmetric spacetimes. Yeah, please.
Massive particles can read scribes, right?
There's no stripe, there's stripe. No, they can't. They go this way.
Why do they bend?
Well, that's the whole point. We can't answer that. We have to calculate this trajectory starting from the original straight line in the original coordinates. So if you want the answer, they bend because of the conformal map. This is an unphysical metric, so they are bent in this unphysical metric.
Okay.
Another thing to say here is, sorry, maybe I don't know if I drew them wrong. They shouldn't be. I think you look up Hawking and Ellis and see what the trajectories look like. I could also do that for you, but it would take me too much time.
Also, what part of this Penrose diagram correspond to the Poincaré patch?
Yeah, good question. So there's basically, so this is tricky because actually then you have to go back to the compactified ADS and take its half. And then in the copies, you have to choose the halves accordingly. I think this is also explained in some references. But since you have asked, why don't you try to work this out, and I'll maybe just remind me next time. I'd like to say a few words about it.
Okay, so are you saying that before taking this universal cover itself,
yeah.
you will have some portion, like half of something?
Yeah, exactly.
Poincaré.
Yeah. So it makes some kind of diamond. Again, Hawking and Ellis actually have discussed that. Okay, now what I was hoping to do, and it might happen next Monday, is to talk about asymptotic symmetries for all the 3 cases. The problem is all the discussions are different, and all of them are, there's no limit to how much time one can spend on them. So this week I'll think a little what I want to do. If it seems like it's going to be too long, then I might instead go to causality right away and leave this for later. But I warn you that anything which is left for later usually doesn't come back. So I don't know what will happen, but we'll find out next week.
Will we be discussing these BMS?
Yeah, so if I discuss asymptotic symmetries, then the asymptotic symmetries of Minkowski spacetime are the BMS symmetries. There also there's an issue, which is that it has a long history. The notations have been very obscure, the discussions have been very hard to follow. Then there are more recent reviews, but then often they are only in 4D or only in 3D. So I'll have to see what I can filter out from all that which is valid for generic dimensions. I'm sure there is something, because after all the discussions we've had finally pick out maybe 1 or at most 2 coordinates to be special, like time and 1 space, and then everything else is a sphere. So the transformations of the sphere, as you know, are part of BMS, but that's sort of in a way the easy part. and then something which goes along the null, scry plus or scry minus, that's a slightly more subtle part. Then there are claims that those symmetries can be extended to infinite dimensional ones, and so there's a lot to unpack.
So we'll be doing for just the flat space time or?
First, well, let's decide whether we are doing it at all. If we are trying to do it, I want to do it for all of them, but one by one. But that will take at least, at the very minimum, then whole of next Monday and Tuesday will go in asymptotic symmetries. I'm sure you won't mind, I won't mind, but it depends on this week, how much time, because this I don't have any notes on. So I have to start making the notes.
And also notes are not, I think, uploaded on the...
Notes are not going to be uploaded on the website. I think I told some of you that. So notes will be given to people who are, I still don't know who's registered or if anyone is registered. I know that almost no one is registered, but is it 0 or is it 1? That I don't know. You are 1, 2, 3.
Hasn't started yet.
Hasn't started yet.
Yes, but 3 of us will be registered.
Okay. Coming from ICER, that's really hilarious. Like, our registration is a military procedure and you get executed in public if you don't do the registration in time. But I guess in TF with a PhD program, they can afford to do this. But there are 3 of you. So if you can all email me for the notes, I'll mail you the notes. And after that, others are free to get them, but you have to get them from somebody registered and you have to promise that person not to put them on the net. I assume that the registered people who are getting them already have promised me not to put them on the net. That's all. It's only because the notes will be eventually published, and so I don't want to have them completely circulating in this form at this stage. They also not, they also have some errors. I mean, there are things which I keep discovering every day. Okay, I hope that's acceptable compromise. Okay, but please, the registered students should mail me at my email address.